uh, we are going to participate in the presentation given by Vincenzo Scott, and which is a series of presentations promoted by the ICT for the Dev. So Vincenzo, in a short, is going to talk about the natural language programming, and in particular, he will speak about how this language has developed to the chatbots. And I think I'm going to give I'm going to give the word to Vincent so that he can introduce himself and start the presentation. Please, Vincent, the floor is yours.
Thank you for the introduction, and thank you for having me here today. So I will start by sharing my slides so I can also spend a couple of words to talk about me. Can you all see the presentation? It should be in full screen right now.
Yes, we can see it.
Okay. So as Juvencio, did I pronounce it correctly?
Yes, very well.
Okay. So as Juvencio said, I'm here to talk to you about natural language processing and how and which are the very recent developments in this field that has become very interesting right now. Basically, I will do a quick recap of. Sorry.
Well, I think the presentation is just popping up sometimes, and sometimes it disappears. I don't know what's going on. Okay. Sometimes we can see it, sometimes we cannot. So it's just popping up and then off. So I don't know what's the reason for that.
I don't know what can I do. I mean, the connection seems to be fine here, so I don't know what's going on. Maybe I can start sharing from scratch.
Yeah, I think now we can see it. Maybe now
Okay.
it's on. Okay.
Okay. Thank you. So
Well,
as I was saying, sorry.
I think I think I have to talk with Elton so that he can. Can you please restart? Just restart the computer. I don't know what can be the reason.
Okay, it may take a while. Maybe I can try to share the entire screen. So
yeah,
is it working better now?
Yeah.
No?
Now it's working better. Yeah, yes.
Okay. As I was saying, I'm here today to talk to you about the latest developments in natural language processing, which has become a very interesting field especially in the last months. And basically what I will do is recap on what happened in the last around 10 years from now. So this is the brief outline we are going to go through. We'll start with an introduction. I will talk to you about vector semantics, the models currently available to process text. And in particular, we will see what are these large language models that everyone is talking about right now. I will explain how all of this connects to the other research lines in natural language processing and not only. And finally, I will conclude with presenting the limitations of these technologies and the next steps or the current hot topics in the field. Before starting, a few words about me. I'm a postdoc researcher in computer science and engineering at Politecnico. I got my PhD less than a month ago. And my research interests are mainly natural language processing and deep learning for natural language processing. I like to work with both text and speech, so not only text analysis. And my current work is mostly related to chatbots and conversational agents and retrieval systems, so like search engine to retrieve relevant information from queries like Google, but using more sophisticated techniques that usually involve, again, deep learning. This was just a joke to tell you I'm not as serious as it looks from the photo, so don't worry. And if you want to ask questions, please feel free to ask. Now, what is the landscape of natural language processing right now? There is a lot of talking about natural language processing. I suppose you have heard maybe about transformer neural networks, even if you don't know precisely what do they are. You have maybe heard of large language models, and especially right now about chatbots. So there is ChatGPT, that is this very interesting technology that is now available, and there are other similar solutions like the Bing Chat that is integrated also in the Bing search engine. And now Google is trying to compete with ChatGPT with its own Bard chatbot. And there are many other technologies like this. What's really interesting about these chatbots is their capability of sustaining very long conversations, and the fact that they seem like to know everything, and they seem to be capable of everything that involves text processing. So they represent a very flexible and useful tool that can be adopted to solve a lot of different tasks. But how did we get there? So 10 years ago, this level of conversation seemed an impossible dream. Now instead we can actually interact with these technologies, and they are amazing. They are incredible. 10 years ago, what we had were mostly formal approaches coming from the computational linguistics research line and tradition. So basically, you will process text as we are used to do with programming languages. Okay, so sorry. Okay. You will process text as you do with programming languages. So you try to decompose the sentence into individual tokens, and you try to understand the meaning of something by building a parsing tree that should embed the meaning of the sentence, or at least it should help decompose the sentence in something that could be interpreted by a computer. On the other side, we had statistical approaches, mainly related to traditional machine learning solutions that involve the text mining and information retrieval. Here in the second picture, I'm showing, for example, we have the results of a topic modeling analysis. These were all technologies that existed more than 10 years ago, even in the 90s, these solutions are available. And they haven't changed from that point they came out on. What really happened now is that we have deep learning. So basically, there was one constant element that hasn't changed in all this time, that are language models. Okay, I will be talking a lot about these language models. They are basically probabilistic models of language. So imagine that your piece of text is a sequence of words. Okay. A language model computes the probability of observing that sequence. Okay, usually you compute the probability of each word individually, and then you get the product of all the words to compute the probability of the sequence. And they have always existed in NLP, even from the start of the field almost. What we can do now is take advantage of the computational power and the data availability and exploit deep learning based approaches. Okay, this is why I was talking about deep learning. Deep learning allows to learn very large and complex models for language that we can use in all these amazing applications that we have right now. So deep neural network, again, have been around for a long time. There were already some NLP tasks that were solved using deep neural network or neural network, simpler neural networks. What happened 10 years ago is that the computational power of GPUs enabled scaling up these networks to a size that allowed to learn something that was actually useful. Okay. Finally, we had enough computational power to train very deep and complex networks on very large data sets. It is important to keep in mind that whenever you're going to work with very large deep neural networks, you must use a sufficiently large data set that can be used to learn from. initially, computer vision was strongly influenced by deep learning. Now NLP started changing as well. Okay, but how can we use deep neural networks for NLP? So this is the start point of this this presentation today. How can we use deep neural networks for NLP? How do we prepare our inputs to be processed by a neural network? In a moment, I will be showing you everything. Just a quick disclaimer, in this presentation, I won't go into the technical details. I like a lot the technical details of this stuff, but these are very complex technologies and they will require a lot of time to present everything, and it's also a bit out of scope. It would require an entire deep learning course to show you all the details of what's going on under the curtains, behind the curtains. It all starts with vector semantics, however. So we need to use deep neural networks. So we need to represent text in a way that is compatible with deep neural networks. The issue is that traditionally NLP and text mining used some representations that were highly dimensional. So imagine that to represent a word, since all words are individual entities, they used vector representations that had a lot of dimensions, like the size of a vocabulary. So imagine a list of numbers of the same size of a vocabulary of a language that is around 50 to 100,000 elements, 50,000 to 100,000 elements. And these representations aren't very informative because they are very sparse and orthogonal. Okay, so even if you have similar words, they are usually mapped to completely different vectors. Why so? The representation appears to be something like the one in red I'm showing right now on the screen. So a lot of zeros and a single element that is set to 1. How does this representation work? Basically, each word corresponds to an index in a vector, and whenever you are trying to represent that specific word, you switch to 1 the value of that element in the vector. Otherwise, all the other elements are 0. So basically, if you have two different words, like let's say hotel and motel, even though they are similar, they are mapped to completely different vectors. If you try to compute the similarity between these two vectors, their distance, their dot product, you will get a value of 0. Instead, neural networks prefer representations that are compact, so way fewer dimensions that are actually more significant. And they prefer representations that are dense. Okay, so points should be well spread across the space and preferably don't have many values set to 0. This is why we try to learn representation for words that are more compact. So we try to decrease a lot the dimension and that are more dense. So as you can see here, the vector in blue, we have many values that are non-zero. Okay, you can have negative values, positive values, but the important thing is that the vector is more compact and values are better spread across the available space. Okay, and this is basically what started the research on vector semantics. Okay, we need to learn this kind of representations. We need to find vectors that can encode words to be used as input for neural networks. And ideally, these vectors should hold the meaning of the word they are representing. So how do vector semantics work? Basically, you learn or identify in some way a spatial representation of words. Okay, each word is a point or a vector in a d-dimensional space. Okay, and you can try to learn this representation so that words with similar meaning are mapped close in the space, or vice versa. So many different words are far away in this space, and the position of vectors reflects the relationship between words and concepts. Okay, so take a look at the figures right here. For example, you have that the vector separating men from women is the same that separates king from queen. Okay. Same thing for the second figure. You have the vector separating the two forms of the verb to swim, swimming and swim, are the same, separating the working and worked. So, for example, in this case, we are encoding the past tense relationship. Okay, we move from present continuous to past. Other things that you can encode and you can learn are, for example, the country capital relationship. Okay, so Italy is to Rome, as UK is to London. You can try to learn a vector representation for words. So basically, you can try to learn different vectors for all the available words in a vocabulary that are placed in the space, so that these kind of properties are valid. What's interesting is that this enables a lot of operations, interesting operations, to deal with the meaning of the represented words. Okay, for example, if these relationships are actually were preserved, you can try to solve analogies by doing simple math operation with vectors. Okay, you can compute the representation of queen by subtracting the vector of men to the vector of king and adding back the vector of women. Okay, so we are removing the component of gender from the word king. We are adding another component of gender that actually represents women, and we obtain the representation for queen. Okay. These are all these kind of operations are enabled as long as you learn a sufficiently good representation. Now, what do we do to learn these representations? We train word embedding models. Okay, word embeddings basically try to solve a matrix factorization problem. Okay, you are given a very large matrix that contains the number of times words appear together in documents. Okay, so imagine a large square matrix, and in the cell with column I and row I and column J, you have the number of times the height word in the vocabulary appears together with the jth word in the vocabulary. You need a corpus to count these occurrences, and basically you learn word embeddings trying to factorize this kind of matrices. One of the first models that tried to solve these tasks, that got famous because it leveraged a very large data set, is word2vec. It exists in two different flavors. You can try to learn, but basically both approaches try to learn two matrices that decompose this co-occurrence count matrix. And there are two solutions to learn these two decomposition matrix. Either continuous bag of words, where you learn the vectors so that you can, by trying to predict the missing word in a text sequence, or you can use the skipgram approach, where given a word, you try to predict which are the most frequent words that surround this one in a given piece of text. You gather a lot of documents, you analyze a lot of documents, you iterate the learning procedure on a lot of documents, and eventually you can learn a word embedding model that holds all the interesting properties that we want from a vector semantic representation. Right after word2vec, other newer and better improved models were invented. I will just report the other main two models. One of them is GLOVE, and it approaches the same problem of word2vec, but from the other side, from the other way around. Instead of learning by trying to predict missing words or surrounding words, it tries to predict directly the co-occurrence count in the original matrix. The results are very similar. You can learn again a newly different word embedding model, and apparently using this probabilistic interpretation that GLOVES suggest actually yields improved representation. So more of the properties that we want from vector semantic models are preserved in a solution obtained using GLOVE. Here in the figure, for example, is a representation, is a visualization of what appear if you try to search for points in space that are close to the word frog. Okay, they took basically the word embeddings identified by GLOVE, they searched for the embedding of frog, and they looked around in the space to see which were the other points that were close. What's very interesting is that basically the model learned representations that actually reflects the similar species of animals that are all part of the family of frogs and toads. And it all did this by simply learning to predict, given two words, how frequently they appear together in documents. Okay, they compute this count by computing the dot product of the two word vectors representing the words, and in the end you can get this kind of representations. So as I was saying, you get in this case around the word frog all words that actually represent similar animals. Okay, so the semantics of the word is correctly captured. Apart from Globe and Word2Vec, another very interesting model that was presented was FastText. FastText built on top of Word2Vec. It tried to improve this model by including the structure of the word inside of the embedding. So let's get back to the example of hotel and motel. In this case, you have the two words are very similar, and even in the structure, so they're just one character away, one from the other. And ideally, this kind of information can be used to build better representations. In this way, you can also manage words that are out of the vocabulary. So in some cases, you get newly word, or you can start from a vocabulary that is not complete. With an approach like that of FastText that also encodes words using the character level information, you can deal with words that weren't in your vocabulary when you learned the representation, and it can be still working. This is something that misses from Word2Vec or Globe. Now the approach is slightly different, but this was a very interesting step forward to generalize the representations that could be also extended. Okay, so this was just a brief introduction on word representation. Basically, the idea is that you need to get vector representations for words to deal with, to perform some kind of text analysis. But the point is that the embeddings, so these vectors that we learn, are static representation of a single word, but the text is a sequence of words. So we need to find a way, we need to find a tool that can analyze sequences of vectors. Okay, so imagine that you have your piece of text. Here is just an example of the incipit of the book The Hobbit. And what you need to do is break down this piece of text into the individual words, map each word to its corresponding embedding that you have learned before, and then you can start your analysis. But you're dealing with a sequence of vectors. Okay, you don't have, like in traditional machine learning, a single vector representing your entire input, but you have multiple vectors that in sequence compose your input. So you need to use tools that can deal with sequences that have varying length. Okay, pieces of text can be of different lengths, of course. And you need tools that can capture long-term dependencies. Okay, so in this piece of text, we have the word whole repeated multiple times. It is always referring to the same whole, and it's the same whole that is mentioned in the beginning of the text. So even though we go forward through the analysis of text, so we scan our text starting from the first word to the last, we need to keep in mind that there are dependencies that can span a very large window of words. Okay, and we need a tool that can do all these things together. Deep learning offers a very powerful tool to process sequences of this kind that are the recurrent neural networks. Okay, so before getting to transformers, we actually had recurrent neural networks. How do they work? Basically, you have your cell of recurrent neural network, which is basically a particular neural network that can manage some memory other than the input in a sequence. And you have this cell that leads through the input sequence. For each input element, okay, so for each X that you see on the bottom of the figure here, that is the element of your sequence, you scan it with the recurrent network, and then the network moves forward. What's important is that apart from the input, you have an additional hidden state. Okay, you have a separate vector that plays the role of memory, basically. What you do is, when you are given your input and your hidden state vector, is to compute the corresponding output. So you get out a new vector that is the output for that current timestamp. So for the current element in the sequence, and you get an updated hidden state vector. Okay, so basically you keep updating this hidden state vector for each element in your input, and eventually you scan the entire sequence. What's important is that the hidden state vector is updated at each step so that you can keep memory of what you saw in your sequence. Okay, so you can move through the entire sequence, you get to a newer element, you get your updated memory vector from the last element in the sequence you scanned, you get your output, you get your updated memory again, and you keep going forward through the sequence. There are different kinds of recurrent neural network. There are the original recurrent neural networks that were very, very simple elements. We have long short-term memory that helped manage the main issue of recurrent networks, that they couldn't learn on very long sequences, even though they are designed to do it. They don't work well in practice. And we have gated recurrent units. They are a simplified version of LSTMs. They work in very similar way, but they are just an alternative. You usually prefer gated units when you have smaller data sets. And what can we do with these recurrent networks? We can build sequence-to-sequence models for text processing. So we can have a model that has a sequence as input and the sequence as output. Remember when I was talking about language models? So we have that a sequence of words in input. We want to compute, for example, in output, the sequence of probabilities of the individual words, so that we can compute the probability of the entire sequence. This is what we use sec-to-sec models for. In fact, in general, these models are designed to take an input sequence and do some computation, predictions, or generation steps to produce an output sequence. These original sec-to-sec models were built using recurrent neural networks. As I will show you later, there are newer, better alternatives now. And they developed also many different variants. Okay, so for example, you can stack multiple layers of recurrent networks. Okay, you can have a first cell that do a scan on an input sequence. You can have a second cell that scans the output of the previous one. You keep producing sequences as output until you get to the final end of your neural network. You can scan the sequence in both directions. Okay, so in the original version, I showed you scan from left to right. You can also, at the same time, scan from right to left. In this way, you can get the hidden vector from the left and the hidden vector from the right. It's more information available to do your computation and to learn to extract a better hidden vector to do your prediction later. Another kind of architecture that you can build with recurrent networks is the encoder-decoder one. Keep this in mind because it will be coming back later. Basically, you can have two separate networks, one playing the role of the encoder and one that of the decoder. The encoder network is a recurrent network in this case that scans the entire sequence and output a vector representation that we call context. And this context is used as additional input to the decoder. So the decoder generates the output sequence and uses a separate information from the context to solve its task. This kind of architecture is was particularly useful, for example, for machine translation. The encoder processes the text in the source language, and the decoder generates the text in the output language. Through the context, you have the information on the text you have to translate. Same applies for question answering or chatting. I will give more precise examples later. So as I was saying, you can use this neural network to learn neural language models. Okay, you can use sec-to-sec models to learn a probabilistic model for language, the one I was mentioning in the beginning. Okay, so the idea is that you are given the current word in your sequence, starting from the first one. You're given your hidden vector, and you predict the next word. So here I'm showing the kind of prediction we want to do. You are scanning a sequence from left to right. So from the current word that is so, in this case, we want to predict the next one in the sequence that is long. So long, and thanks for, then the sentence is complete. What you do is then keep on scanning your sequence. So at each step, you use all the information from the left side of the sentence to predict the next word in the sequence. What's the advantage of working in this way is that you can have your model then generate new text. Instead of using the next word from the sequence to do the learning step, as I just showed you, you can use the current word to predict the next one. So you sample the next one from the output from the output distribution from the neural network. You attach it to the sequence you are scanning with your network, and you can keep on generating new words. This process is called autoregressive generation. Basically, you start from a model that has learned to predict the next word, as you can see on the left. So at each point, the network is trained to say which is the next word in the sequence, which is the probability of observing a specific word as the next one in the sequence. Then you can, once you train these networks, you can use them to actually predict new text. Okay, you can generate by sampling the output distribution. For each word, you get the probabilities of all the other words in the vocabulary to be the next one in the sequence. You can sample this probability, extract a new word, and attach it to your sequence to keep on to keep generating the text. Okay, and these techniques, these recurrent networks, were widely used in translation. Okay. So in translation, as I was saying, you usually work with encoder-decoder approach. You have the source text scanned from the encoder and the target text in output to the decoder. What you do is take the last hidden state of the last hidden state of the encoder. This is an output vector that is used to initialize the decoder. The decoder starts generating the translation by using the information encoded by the encoder. Notice that we are compressing this entire sequence into a single vector that is then used once here in the beginning of the decoding and is not used anymore. So researcher thought it was a better solution to avoid losing information from the context, to not only start the decoding with this additional vector, but repeat this vector as additional input to each cell of the network. So at each step, you have the current word in the translation, okay, the newest word in the translation, but also you repeat the hidden vector as additional input, the hidden vector coming from the context. In this way, you can keep more information in memory to help guide the translation. The point is that the question that then arose was, is a single vector good? So I'm still compressing the entire sequence into a single vector. Is it still good and useful? As we will see, no. The problem is that it's still not sufficient because you are trying to compress too much information into a single representation. So keep this example in mind because it will come back in a few moments and you will see what you can do to improve the capabilities of neural network without changing too much the architecture. What I wanted to show you as the last example on recurrent networks was that even with these networks, you can build chatbots, okay? So you don't need very large transformer networks. You can do it with recurrent models. But the quality is, however, lower. There are better techniques to build these models. But the principle is the same of translation. You have a source sequence, for example, the context, the last messages in the dialogue, and you have a target sequence that is your response. Okay, you start from the last sentence that one of the two speakers said in the dialogue, and you generate your output. There were different solutions proposed through the years, use only a single network, use an encoder-decoder approach. Other more sophisticated try to embed a separate context vector information on the two speakers. Okay, to make your chatbot more consistent, you can say, okay, just keep in mind that your name is this one, you're talking with this other person, and you can embed all this information into a separate vector that is an additional input to your neural network. So when you decode, you know that you have as input the sentence you are generating, and you also have the context that describes which are the participants to the dialogue, for example. The problem is that recurrent networks have some flaws, and for example, the fact that they scan the input in a sequential manner slows down training. So you can train for too long, or you can train or on too large data sets, or it will take too much time. And in the end, you can't manage contexts that are very, very long. So at some point, the network starts forgetting the first parts of the conversation. And with respect to more recent technologies, it does it very, very quickly. The result were very dull chatbots that kept repeating the same sentence over and over again, or kept replying, I don't know, to every input from the user. And these were the main reasons that led to the development of the kind of networks we have now. So the development of attention mechanism and transformer neural networks. What is the point behind attention? We need a way to avoid losing information from the input, so we can't keep compressing everything into an entire sequence into a single vector, and we need to find a way to better align the input and the output. So we need to find a way to exploit better the content of the source sequence, for example, the sentence to be translated or the last message in a dialogue, to generate a better output. So the idea behind attention is that we can have the model learn to do these kind of things. So it seems that even before we were trying to ask the model to do it at some point, but with these newer architectures, we state this problem explicitly to the network. Instead of relying on a single fixed context vector, we can compute many different context vectors for each element of the output we are generating. In this way, we can adapt the input to the current output we have produced, and we can reuse better the information from the context. And this is where this is exactly what attention mechanism does. Okay, so basically, remember the encoder-decoder architecture. From the encoder, you produce a sequence of hidden vectors that are updated at each step. You can save all the hidden vectors you produce, and you can basically use all of them to generate a context to be used by the decoder. At each step, the current hidden vector of the decoder says which information to retain from the encoder. How does it work? Basically, it does a weighted sum of the hidden vectors from the encoder, and use it as in the same way we used before the single context vector. Whenever we change a step in the decoder, we generate a new context. At some point in the decoding, we try to generate the new context. So we compute the similarity, in this case, between the hidden state of the decoder and all of the hidden states of the encoder. Okay, this similarity score defines the weight we need to use when summing together the elements of the encoder, the hidden vectors of the encoder. And in this way, we extract a new context. Since these weights change every time we move in the decoder, we will get every time a different context. At some point, at this point, we can generate the new element in the output by using the current input, the hidden vector from the decoder, and the context vector computed from the encoder. Again, keep in mind, this context vector is dynamic and changes at each step of your decoding. In this way, you can exploit better all the information you have acquired from the encoder. And you're also separating the analysis of the encoder from that of the decoder. So you're generating text through the decoder. This is why you use the memory vector from the decoder, but you're generating text to solve a task connected to an input. This is why we use the context vector. And this kind of approaches was first introduced for translation. Okay, this is why I keep doing a lot of examples on translation. It also helps understand better what is the role of the attention. So take a look at the matrix here on the bottom right. This is the alignment matrix of the translation between French and English. Each row of this matrix contains the attention weight used during the decoding. Sorry, not each row, each column. So we are translating from French to English. Each column contains the attention weight to generate the translation. So when we are generating the first word, the article "de" in the English text, we have that all the weight. So the brighter part of the column is focused on the "le" from the French text. Okay, and this is actually correct, since in this case the translation is one-to-one. This article is directly translated into the English text. And basically each column here represents the weights. So basically it says how much the corresponding word in the corresponding word in the original text has influenced the generation of the output translation. So in this case, agreement and accord are strictly connected. In fact, the French word accord basically translates to agreement, and so on. What is really interesting is that, for example, the network now starts to understand that since the two languages places the words in different order when they do the generation of the translation, you have also to reorder the alignment. So instead of having a perfectly diagonal representation here in the attention matrix, you have some parts that are actually inverted. In fact, European maps to European correctly, but European appears first into the English translation than the French one. Okay, this zone economic European is translated with inverted order in English, European economic area. And this is why we wanted, this is exactly what we wanted our network to learn. Okay, so give different weights to the different word in the encoder, depending on the one you are trying to generate through the decoder. And in this case, it is actually learning that this alignment corresponds to the translation alignment. Okay, the corresponding words or pieces of text that maps from one language to another. And this is the role of attention. But what was really interesting is that in 2017, some researcher from Google asked themselves, but what if we apply attention using the same sequence as source and target? So in the translation, we have two separate sequences. One is the source, the original text. One is the target, is the output text with the translation in the desired language. So these researchers at Google said, but what if we try to align a sequence with itself? Okay. Basically, you can build a stack of attention transformations where you keep computing weighted sum of your hidden vectors and update these sums at each transformation. The interesting part is that the alignment in this case, so the attention weights start to learn the relevant syntactic, semantic, and lexical relationship. For example, in this visualization here, we have that the pronoun it is referring to low in the input text, actually is mostly connected to the word low. So actually, the attention mechanism when going from one step to the other, saying, okay, when you build the new hidden vector of the word it's, remember that it mostly the meaning is mostly due to the word it is actually referring to, that is low in this case. And what's interesting about this approach is that we can get rid of sequential model in this case. Attention can be computed completely in parallel. This increases the memory requirements and the computational power requirement, but we don't have anymore the blocking sequentiality of neural networks if we work in this way. So we can exploit better the hardware from GPUs I was mentioning in the beginning that is designed for highly parallel computations. Okay. And this is basically where transformer neural networks were born. So when they started applying attention on a sequence on using the same sequence as source and target, was the definition of the transformer neural network. And these networks came as drop-in replacement of recurrent networks, so they can completely substitute recurrent networks. Here on the right, I'm showing an example of the original transformer architecture. It is again an encoder-decoder architecture, and it uses attention in multiple points. So this is the self-attention in the encoder. This is the self-attention in the decoder. And you also have cross-attention to align the input and the output you are generating. Here, these boxes you can see here in gray are the blocks of the transformers. Each transformer network is usually composed of multiple blocks. The blocks alternate self-attention transformations and nonlinear projection. You can build a very complex network that stacks all these transformations together. As I was saying, we have an encoder and a decoder. What's interesting is that the structure of the input is very similar, but not quite the same of that used for recurrent networks. In fact, since we are doing all the computation in parallel, now we have to build the input as the sum of two embeddings. The original word embeddings we were already using, and a separate embedding that says which is the position in the sequence. Apart from that, that basically alters only a bit the input. We can use them in the same way we use the recurrent networks, but with improved utilization of the computational resources, because now all the computations can be done in parallel. Again, I'm referring a lot to machine translation because this network was originally developed for machine translation. It was designed to solve translation from one language to another. However, they are perfectly compatible with generic language modeling task. Okay, so prediction of next word in the same sequence. Sorry. Okay. But sorry, as I was saying, We can use them for generic language modeling, and we don't need to use necessarily the encoder-decoder architecture. We can use the autoregressive decoder model that basically works as the original recurrent networks. So it scans a sequence from right to left. You obtain this sequentiality by altering the vectors that are used in the computation of the attention. So when you work on the first element, you map it to it. You use attention only on the first element. When you work on the second element of the output, you use the attention on the second and the first element. When you compute the output of the third element, use the third, the second, and the first, and so on. In this way, you are building a representation that is also causal. So it shifts information from left to right. Alternatively, you can work with bidirectional encoder models. This is the same of the bidirectional recurrent networks. You can use attention to look at all the direction in your input sequence, so not only from left to right, but also from right to left. And basically, the solution is the same. You keep updating through attention the hidden representations of this sequence of text. These embeddings are continuously recomputed through the attention mechanism until you reach the output point of your network. As I was saying, all the variants of this transformer network can be used for language modeling. The task changes a bit. So when you work with causal transformer network, you actually work with the usual causal language modeling, so predict the next word in a sequence. When you work with bidirectional model, since you already have access to the rest of the sequence in input, what you usually do is doing masked language modeling. So you corrupt the input sequence, you hide some of the input vectors, and then you try to predict which are the missing vectors in the sequence. In both cases, you obtain a language model. Why do we train all these different models for language, especially the transformers one? We need to use them, and we want to use them to solve many different tasks. For example, we train to solve many different tasks. We start from what we call pre-training. So we get an incredible large data set, and we train the network to do language modeling of these incredible large data sets. It works better if you use different data sources, so different kind of documents from Wikipedia articles to books to, I don't know, even web forums and so on, and different domains. So you want to space also a lot in the arguments of these documents. If you collect a very large data set of this kind and you train especially transformer network, you obtain a very powerful language model that can be adapted to solve many different tasks. Okay, so you can reuse this model as initialization, and then you can refine it on a specific task. For example, you can this process is called fine-tuning. You can start from a pre-trained model that analyzes both French and English, and you can refine it to do machine translation. So you keep training your network, but in this case, in the second step, in the fine-tuning step, you only give data on the specific task you want to deal with, for example, translation. Through the years, multiple different language model transformers were proposed. One of these is I will just mention the most famous ones. The first one was BERT. It's a bidirectional encoder trained to do masked language modeling. Here is an example of input to BERT. It takes the word embeddings, it takes the position embedding, but also the segment embedding. It's an additional embedding used as input to tell to the model which part of the sequence is scanning right now. It was one of the first transformer-based neural language models, and it helped improve the state of the art on many different tasks. Basically, it is used in the end. It is used mostly on classification and labeling tasks, but it is a very generic language model that can be adapted to solve many different NLP problems. In the original paper, they showed how it could be used to do question answering, to do sentence classification, for example, sentiment analysis, and so on. The main alternative to BERT was GPT. This is the same GPT of the ChatGPT we are all talking a lot lately. Now we have arrived to the fourth iteration of this model. The original model defined the architecture that has been preserved in all these years. Basically, it's a causal language model. Okay, so it's a language model trained to do next word prediction, and that's all. It's trained on this very simple task. And what's interesting with respect to BERT is that it works well as a text generator, other than the fact that it can be fine-tuned to the same tasks that BERT can solve. So why did GPT evolve so much while BERT was left behind, let's say? The point is that when they started evolving the GPT system, they began to notice very interesting things. So as soon as you reach really large size of your neural network and you train it on a very large data set, you can see that the models start to learn multiple tasks directly during the pre-training, and that the quality of the generated text is very high. So you can use actually as a generator to produce text that seems produced by humans. The last model I want to mention on this list of language models is T5. So we have seen an encoder, a bidirectional encoder model that is BERT. We've seen a causal decoder that is GPT. T5 goes back to the original encoder-decoder transformer. Okay, so it uses actually two transformers that are connected together by an additional attention layer. The difference with respect to these two models is that it is trained on a completely new task that is called span replacement. Okay, so you take the original piece of text, instead of removing individual words, you can remove entire passages and ask the model during training to reconstruct the missing passage. Then you can fine-tune it on the task you prefer. What's interesting about T5 is that it was one of the first models to scale over the second GPT neural network. It started pushing towards very large data sets and very large models. So we are talking of tens of billions of parameters. And it's also pushing a lot towards multitasking. Okay, so a single model can be fine-tuned on multiple tasks at the same time, and it preserves the capability to solve all of them. Okay, so we are going to the point that we have reached right now, where a single model can do almost all the possible tasks that NLP offers. Before going on, I just wanted to show an example of how these transformer language models can be fine-tuned to become chatbots. So you can start from your language modeling pre-training. What you can do is then keep on the training on dialogue data. Okay. In the example here, I'm showing that you give as initial input the context that is composed of the previous utterances in the dialogue and possibly additional information on the speaker, similarly to what we saw in the other example with the sec-to-sec model. And you train your model, so you have your model learn how to generate a response, so the next turn in the dialogue. This is even closer to language modeling than it was with sec-to-sec models. An important thing I want you to notice is that differently from sec-to-sec, where we compressed all the information in single vectors to be used as context, here the computation is done on the entire sequence. Okay, we have a causal transformer model that every time it generates a new token, it looks back at all the elements of the input sequence. Thanks to attention, we have that all the hidden transformations that are done here take into account all the previous tokens that were in the sequence to compute the next one. While with recurrent networks, we had a single vector that compressed all the sequence. Here, the model can span indefinitely backwards into the input to generate the next step in the output. And this is the main reason why transformer-based solution yielded better chatbots. Although at this point, they still weren't as good as the models that we have right now. There was still a missing part. And this is where large language models arrive. At some point, they noticed that, okay, the architecture seemed to be well-defined. We can use the transformers to do a lot of things. We need to scale up. We need to increase more and more the size of the network. We need to increase more and more the size of the data sets. Okay, so the objective became to scrape the web for insanely large data sets and train insanely large transformer networks on this data set. The task remained the same. We are still dealing with language models. We are just getting all the data we can get. And we are in the last years, starting from 2018, we have seen a general trend that was, okay, I collect more data, I train larger model. Collect more data, train larger models. So all the big players like Microsoft, Google, Nvidia, Facebook started started training larger and larger models. OpenAI seemed to have blocked the bit after GPT-2 until they decide to work on GPT-3. So this is what they did. On the graph here, sorry, on the graph here you have the with respect to the time period, the size of the neural network. So GPT-3 said, okay, I want. With GPT-3, the people at OpenAI said, we want to train the largest model possible at this moment. So notice how fast they get to hundreds of billions of parameters when the previous larger model was a few tens of parameters big. What's the interesting thing about going with the network of this size? Well, you create something, they created something that was the first of a kind, that of large language models. They increased significantly the model size and the complexity. Notice that here the scale is logarithmic, and it is comparing the number of training operations required to do a day of training with respect to different size models and architectures. And they used an insanely big data set. Okay, so here in this table, you can see the number of tokens consumed by the model and the different sources. Notice that only in terms of books, it read more than 60 billion words in total. Okay. If you consider that a book is around 100,000 tokens, if you read the book every day for around 2,000 years, you will get to the same point where GPT-3 was when it finished its training. Okay, so it read a lot of books. It read all the internet basically, and this is why it is so good. It is an insanely large model, so it has the complexity of learning very complex structures, and it was trained on sufficiently big data so that it can extract and use all these complex structures that are present in text. And when we got to this point, we finally saw what was really interesting that we can do with these models. Okay, that is few-shot learning. So someone has the microphone open. Can you switch it off? I hear my voice echoing in my head. Thanks. So that is the few-shot learning. Okay, sometimes it's called instructing, prompting, context learning. The idea is that you use natural language to describe a task and provide the input to the model, all in the same sequence. Okay, So you can tell your model, translate English to French, give the English prompt, and use autocompletion by generation to obtain the French output. You can add more example in the context to produce better translations. So the model generates, taking into account the description of the task, okay, and other examples. This is why they call it in-context learning. It learns from the description and the context, the task to carry out, and then it generates according to the task. So at this point, we have reached that we have very large language models. We have reached a situation where the quality of generated text is impressive. It works with many different languages. The results on all benchmark of all these large language models that follow GPT-3 are impressive. And the interesting thing is that they don't need fine-tuning. Okay, you can basically reuse the model as is after pre-training, and only through text you can instruct it to solve all the different tasks. So the application seems to be countless. In fact, right now the objective has shifted from generalizing on a new sample for a given task to generalize directly to a new task. Okay, these are very interesting times for this kind of research, especially for this kind of possibilities. And finally, we reach the point where we have large language model-based chatbots. Okay? So the current trend now is to use these large language models that can produce very high quality text to be used as chatbots. Okay, sometimes they do additional fine-tuning for dialogue, but it's not mandatory. You can use a prompt for dialogue and it will work as well. You can do fine-tuning to adapt to human preferences, but the point is that these models can be finally used to deploy very impressive quality chatbots. Okay, 10 years ago, this seemed a dream at most. We have advanced so much that now there are even competitions where you have human and automatic evaluation to judge the quality of these chatbots. And this is what basically led to ChatGPT. Now I've taken a lot of time, so I will skip through the advances in other research lines. But what I wanted to do is just talk a bit about the limitations of these technologies, and then I will leave the stage. So first of all, even though these models generate a quality text, it is not you are not assured that the content is always truthful. Okay, this model can hallucinate. To which extent this is an issue depends. If you are using it to write a fiction novel, it's nice that it hallucinates. If you're writing a newspaper article, maybe it is better not to hallucinate. They can be used with harmful intention, for example, the generation and spread of fake content on the web. They may contain bias and unfair behavior. Okay, from the data sets, this model can, since they are frequentist models, they can extract some bias or unfairness that can then affect the output and produce possibly harmful content or offensive or controversial content. Also, there is the big problem of explainability. Okay, it's still hard to explain why a specific output was generated. There are techniques that help the explanation, but we don't have something that works well 100% of times. Now, which are the hot topics and the next steps? For example, many companies are integrating large language models in their services. And this is a research line that for example, search engines have already started doing so. We need to work on improving the accessibility. Now, the hardware requirements of large language models are still incredibly high, and also we need to improve the software accessibility to these models. They are currently only available through APIs, only in some web APIs, only in some cases. Eventually, we will stop fine-tuning, so we need a way to be sure that the model does not need fine-tuning anymore, and that it can generalize well on all the other different tasks it may have not seen during the pre-training step. There are people using these models for data generation, so you don't have a data set to solve a specific problem, to learn a model for that specific problem. You can ask these large language models to generate text data for you. And finally, we need also to identify a new benchmark. So these models are capable of multilingual, multimodal, and multitask learning. They show all these capabilities at runtime. We need a way to correctly evaluate them. For example, in the USA, the ChatGPT and GPT-4 took the bar exam and actually made it to law school. So we need to define a better way to do this, the evaluation of these models. Okay. So thank you all for the attention and for the patience that you showed hear me talking about this stuff for an entire hour. If you have questions, I'll be pleased to answer.
Thank you very much for your presentation, Mr. Scott. Please, guys, now it's time for questions. Maybe I will start. You talked about neural networks, how they are used to build the chatbots. Can you please say anything about the relation between regular expressions, automats, with neural network? Is there a relationship? Any relation between them?
Actually, no. Regular expression and automata come from the traditional approaches to NLP, like those related to formal methods and formal analysis of language. These approaches are very good if you want to be highly precise. For example, when you are trying to extract information with the regular expression, you write your expression, you know that it works every time 100% on all the things that matches your expression. Neural network goes in another direction, let's say. So you maybe not be 100% precise, but you are more robust to noise. So for example, if some information in the text is not written perfectly correctly to match the regular expression, then the regex won't match it. A neural network can have a match in this, even in cases where there is an error in the input, but they are more unpredictable than a regex expression.
Thank you very much.
Yeah, you're welcome. So someone raised the hand to ask a question.
Hi, Vicente. First of all,
Hi.
I would like to congratulate you for your presentation. You are pretty awesome. Yeah, and also the jokes that you put there. So funny. First of all, I would like to ask, during your presentation, you mentioned that the construct language model has not changed in all this time. I would like to know is there a reason behind it, and is it possible that in someday it can possibly change? That is the first question, and the second one is regarding the natural language processing. Since it's a branch of AI, what if I would imagine okay, I want to get into natural language processing. So first of all, am I supposed to learn about AI first, like getting to know exactly what is AI so that I can then go to the natural language processing? And also, what is the relationship between AI, machine learning, and natural language processing? I hope you got my point. Thank you.
Yeah, sure. Okay, so first of all, about the language models, the reason they persisted for this time is that the language modeling is a very clear task. Okay, so what changed is the technology to perform it, but at some point you still need to build some sort of probabilistic model or another formal model to analyze to analyze the text. Probabilistic models are, let's say, more robust to all the variants that you can find in text, while formal approaches that once we used more often than probabilistic ones are less robust to noise. So you must be very precise in describing what you want, and whenever something goes off the tracks, you can recover from this kind of errors. So I think that language models will still be there for a long time. Hopefully, we can find newer technologies to produce even better language models. About the question on NLP and AI, well, I will start with the last point you made. So first of all, AI, it's a very large research area. NLP is a subset of this research area. So you have, for example, computer vision that deals with image and video processing. NLP instead deals with text processing and also with audio and speech processing. So they are all fields that compose the macro field, the macro area of sorry, they are all areas of the macro field of AI. Machine learning instead is not well, is still a research area of AI, but machine learning actually identifies the set of frameworks and tools to create AI, okay, to build AI powered solutions. And about what's better to start learning, well, the AI area is incredibly large, so you have to start from some point. So at some point you will need to decide, okay, I'm interested in this topic, so I will start from this one. For sure, right now, I would recommend studying machine learning and deep learning. All major research areas of NLP, of AI are mostly work on machine learning and deep learning powered tools. So I will say first build a background on these technologies. You don't have to know them perfectly, but start from that point and then try to search what is the specific area you prefer, if it is language or vision, for example. I hope I answered all the points.
Yes. Can you please recommend me some how can I say maybe links or courses to get started with AI?
Links to get, sorry?
To get started with AI.
Okay.
Yes.
So there is a book entitled Artificial Intelligence: A Modern Approach, and another one that is called Deep Learning. Okay, these first two books allow you to build a very strong background on all. The first one is generic on all the AI, the entire AI field. The second one is for machine learning and deep learning. So for sure, these two: Artificial Intelligence: A Modern Approach and Deep Learning. Then, if you're interested in natural language processing, there is the book Speech and Language Processing from a famous professor in Stanford, two famous professors in Stanford, Professor Juravsky and Professor Martin, that is very useful to start learning NLP.
Thank you so much. Thank you so much.
Okay. So, Caesar, I saw that you wrote me a message. I'd like to know if there is any difference between OCR and NLP. Okay, so OCR is one of the tasks and problems that you can find in natural language processing. Basically, it's similar to a translation problem. Okay, you start from an input image and you want to translate it to the text that is contained in the image. Okay. Other questions?
I guess there is no more questions. So once again, I would like to thank you for your wonderful presentation and wish you a very good career in that field. And I think we can end our talk now. Thank you very much.
Thank you for having me here. Actually, thank you very much.
Okay, see you in the future. Bye.
See you. Bye.